Kessler 1-1, Mojave Tower, roger. We'll line up and wait, runway 30, report when ready.
Okay, Kessler 1-1, flight, line up and wait.
Three up and locked.
Clean. Out of burner coming right. A little choppy in the band by the mountains, but nice and smooth now.
Kessler 1-1, ultra flight of R2505 is approved at or above 10,000.
Test control, we have flutter clearance and your go for an Excel to 0.8 Mach.
Copy. All right, rolling out, starting the Excel. Our profile's complete.
Test control, your go to load profile 2.
Copy. What I'd like to do is the flying qualities block here, and then that way we'll run the profile 2 pointed back toward Mojave.
That sounds good. Test control, I've got you on card 10 and your go for a pitch doublet. Test control, we're going to look for 167 on approach.
Copy.
You're on center line. 40 feet, 30 feet, 20, 10, 5.
Okay, whenever you're ready.
Rolling.
Hey boys and girls, I'm here with Blake Scholl, and in back of us is the Boom aircraft. And today we're going to hear a lot about the advancements, if you like, in Boom's new strategy and whatnot. But before that, Eric has asked us to give a little brief history of how we got here, and Blake's going to give you a history on that. So Munro Associates has been involved with aircraft since I worked with Aerodynamics on the F-18 flight controller. Since then, we've worked on a lot of general aviation aircraft like Cirrus, Piper, a bunch of those types of folks, and we actually even designed our own. We had a plane called the Paradigm. Would have been a great idea, but unfortunately our benefactors was Lehman Brothers, and it was in 2008. So we all know how that story ended. Munro was on the was the lead consulting group on the 787, and we worked on pretty much every major aircraft that Boeing and Airbus had. So that's our background. But what I'd like to hear about is Blake's background, and I'm just surprised to hear that you actually started as a tech guy. You weren't in this at all.
Yeah, no, I don't have the resume to work on supersonic jets, really. I'm a software engineer by training. I had my first job at Amazon when my family thought it was a bookstore. Like, we got you computer science degree, Blake. Why do you want to go work retail? But
Yeah.
that was 2001. It was a pretty special time.
Yeah.
But I think I was lucky to grow up in a world in tech where well, that never gets old.
So that's your chase planes, right?
Yeah, that's right. That's a T-38, and whenever we fly the XB-1, we got one of those flying in formation with it.
Well, here's the extra. Here's the second.
Yeah. So anyhow, yeah, I think I was lucky to kind of be in the tech world where innovation was normal, and I look at flight. You know, in my 20s, I toured Concorde in a museum up in Seattle.
Oh yeah.
And I set a lifetime goal of flying supersonic. I put a Google alert on supersonic jet, and I thought, surely, someone would go crack the nut and picking up where Concorde left off. But it was like 10 years of crickets, and I've come to believe that we're living in a dark ages of flight, and nobody knows it. Since the first jets, we haven't done anything for speed, and the whole point of an airplane is to get you from point A to point B, and we're not any better at that than we were in 1969.
Well, at the end of the day, a lot of that has to do with governments. I mean, supersonic. Oh no, the sonic boom, it'll, disturb a cricket or maybe a bird will get caught or whatever. Everybody seems to be so, reluctant to do anything. And governments control pretty much everything. And it doesn't matter whether it's the United States or Europe or whomever. We just seem to be held back.
Yeah.
And it's not just jet aircraft and supersonic. It's pretty much everything seems to be held back. So I'm really excited to hear about this. I really, really am blown away that you actually made something. And you said 50 people in 10 years and you got to this far. This is like amazing. I'm really impressed. Give us a little background on that.
Yeah, well, so this is the XB1, and it's basically the subscale prototype for the airliner that we call Overture. And Overture is the supersonic airliner that we hope everybody gets to fly on. And so it's just to give you a sense of that, it's basically, if you could fly business class today, you're gonna be able to afford to fly supersonic on Overture 1, and there'll be an Overture 2 and Overture 3. The same way Tesla went from the Roadster, this is like our Roadster, down to the S and then the 3 and then whatever comes next. We're gonna keep getting the cost of supersonic down such that ultimately just about anybody can go fly supersonic. But before we go build a 400,000 pound safety critical supersonic airliner, we wanted to prove to ourselves that we actually know how to do this, and we know how to do it efficiently with a small team. And so we took the original design of the Overture airliner, we shrank it down to 1/3 scale, and just like the Falcon 1, we said let's go figure out how to really do this.
Yeah.
And you know this. Anytime you study something on paper, you can always convince yourself it's great. But you have to go build a real vehicle and fly it. You have to learn 100% of the lessons and solve 100% of the problems. And so that was the idea of XB1. Let's go make sure we know 100% of what it takes to build a safe, for humans, supersonic jet out of airliner-ready technology, and that's what this is. So this is the first ever supersonic jet built outside of a government or military. Previously, it's been, actually, this is the first time a civil supersonic jet's been built in the U.S. That's been Europe and Soviet Russia, and we've had military supersonic jets. We've never had a civilian one.
Wow.
And this is so it's smaller than the Overture, but it's built out of the same basic technology. So it's everything you see painted in white is carbon fiber composite.
Yeah.
Very similar materials to what you know from the 787. It's got digitally optimized aerodynamics. So we did a little bit of wind tunnel testing, but the vast majority of the aerodynamic development of this was all in CFD and simulation. And then it's got our Concorde is famous for that droop nose.
Yeah.
That we get out of the way so the pilots can see the runway. And on XB1 and Overture, we solved that with a camera and a screen. So
yeah.
I joke sometimes we've got the first practical application of augmented reality, and so this airplane lands on a screen.
Well, it's funny. I've been trying to talk NHTSA, the National Highway Safety, the Traffic Safety Organization. I've been trying to talk them into getting rid of wing mirrors. Everybody wants to get better fuel economy. We'll get rid of the one thing that continuously causes a tremendous amount of turbulence, and they won't do it. I want to go to mirrors. I want to get rid of mirrors, I should say, and go to cameras. You're going supersonic, and it's okay, but we can't put it into a car.
It's ridiculous.
So it is kind of like
no, it goes to very often regulation can be a one-way door.
Yeah,
and once it's in place, nobody ever wants to be the person that took it out and then somehow there was a mistake.
Yeah. Well,
and that's we need to find. I think we need to find a way to take smart risks, and in the current system, it's very difficult to take risk.
Well, for me, the biggest risk is no risk.
That's right. The biggest risk is staying at home and not doing anything and not making any progress. People often ask me, like, why in the world would I do something so risky, like start a supersonic jet company? And in my mind, the riskiest thing is spending the rest of my life wondering, what if I tried?
Exactly. And I think Elon Musk gave me a shirt, or somebody. When I was at Tesla one time, gave me a shirt, and it says success is an option, and that's true. The option of failure is one that everybody wants to talk about, but fear of success is the most prominent fear that I see in most companies. They just are scared to death that something might go wrong.
They're scared that something might go wrong, or it might upset the status quo. Like, why does Boeing not do this? The biggest reason is, they for 50 years they've been building, 3-class airplanes, first and business and economy, and right now you could do supersonic, but you can only do it kind of first and business, and so it breaks the basic mold of how you think about an airplane economically, and it would undermine the sales of 787s and 777s, and without a visionary leader, no, everyone's afraid to upset the apple cart.
Yeah, well, visionary leaders at Boeing are in short supply. I don't want to go down that path too much, but I will tell you that when I found out who was on the board, I don't know who invented, well, let's have movie stars or athletes or something. That just, I just about shit my pants when I saw that.
Yeah.
And you can't have leadership with people who are either financial or legal or what have you. They don't have the right wherewithal.
Yeah, I think that's right. I mean, the Boom board, we've got Phil Condit, who was the chief engineer on the 757 and father of the 777, and I think actually probably the last really good CEO over at Boeing. And we've got the former CTO of Lockheed. And it's like, great, those are the kind of people that I would surround myself with.
Yeah, and that's kind of what you need. You need to have people who are a success, not, failure. And quite frankly, when somebody comes along and says, well, we're going to put this guy in charge of the company, and you look backwards, well, let me see. He was in charge of hardware stores or something, and that failed. And he was in charge of this energy company, and that failed. Oh, let's put him in charge of a car company. Oh, that'll make it much better. And that failed too. So at the end of the day, having the right board is really important, and having people who are willing to take risks on a board is really
that's right.
Yeah.
My
and knowledgeable as well. That's the other thing.
Mm-hmm. Yeah, knowledgeable and willing to take risk. And all my experience in boards has been when things get hard, that's when you really find out whether you got a good board or not. As there are things like Boom are sexy to be around, and when things are going well, everyone wants to be part of it. And we run into something that makes it hard. Okay, some people run for the hills, and some people roll up their sleeves. And the latter kind, that's the kind you need.
Yeah.
Yeah, I think my hope is what we do here inspires a lot of people. Say like, if this crew of about 50 people could go build a supersonic jet, what else could be done? And I don't think we've got a monopoly on good ideas in airplanes. And my hope is other entrepreneurs will think bigger and go do things that you might not always think are possible.
Well, certainly it worked for you and Tesla anyway. So I believe in small crews that are totally devoted. I really think you got what it takes, as they used to say, the right stuff.
Yeah. No, I completely agree with you. I think small teams of great people can do things that big, theoretically experienced teams might not even try to do, let alone succeed at.
Yeah.
I find that wherever I look in the world and say something great was created, well, you zoom in far enough, you find like kind of 3 people did it.
Yeah, and that's usually 3 people usually started, and an awful lot of other people to try and glue everything else back together. By the way, in back of us, we're loaded. This is like a museum of older aircraft.
Yeah, so we share facilities here with the National Test Pilot School. So the test pilot training of various sorts is done on all these airplanes. And so the two business jets in back, those are used for high altitude upset training. To just train pilots what happens if you're super high altitude and you get into a stall or get into some unusual attitude, how do you get out of it?
Yeah. Are these the ones that are in that plane, your plane?
Yeah, they are actually. Yeah. So these are J85 15s. So these are off the shelf, basically fighter engines. These are off of the Canadian version of the F5, CF5, and so this is what we have on the XB1. And Overture we're actually doing with our own powertrain, which is modern turbofan with no afterburner. People often think you need an afterburner to go supersonic. You don't. You just need more thrust than drag. Yeah. As long as thrust exceeds drag, the airplane's going to accelerate.
So these are a GE engine, correct?
That's right.
Yeah. So and that's going to be your primary engine for the next generation. Oh no, you're going to make your own.
We're
engine.
going to make our own engines. Yeah.
Yeah. So that's interesting.
That's right. Can you imagine SpaceX if they hadn't built their own engines, and they'd gone to Aerojet or somebody and said, give me a rocket engine. They think about it for 5 years before they can even decide whether to do it. Then they'd probably offer like a warmed over space shuttle engine or something.
Yeah.
And so we famously flirted with some of the big guys, then ultimately decided we're just going to take this in house and do it ourselves. And so we're building, it's sort of a conventional technology but custom designed turbofan engine called the Symphony. It's about a 6-foot diameter engine, kind of medium bypass ratio. So it's got enough bypass on it to be quiet for takeoff and landing. Being quiet is one of the hardest things about supersonic jets. But it's got enough core flow and enough thrust to go Mach 1.7 without an afterburner. And so Overture's going to have 4 of those. And we actually just started making the first parts for the first Symphony. And so about a year from now, we'll be making thrust. Yeah, people said a startup couldn't build a supersonic jet. Well, there it is.
Yeah.
And people said a startup couldn't build a supersonic engine. So in about 12 months, we'll find out whether that's true.
Well, I'm really impressed. I love it when I see what we used to call American ingenuity. They got other bad names for that kind of stuff now, but at the end of the day, I'm really, really impressed. I'm glad that you're going because I am a firm believer and have been forever on vertical integration. And the more you hand out, the more you basically are kissing your future goodbye. So
yeah, that's right. And we experimented with that on XB1 of like what should we do in house and what should we do out of house.
yeah.
And we did some things one way and some things another way. And the lesson we learned virtually every time was if there was an off-the-shelf part we could just buy that works, great, just do that. But if it's custom engineering, every single time we're happier if we did it ourselves. You know, like the thing that's gated XB1 Go and Supersonic is something called the flutter excitation system. And we went with a third-party, a brand new third-party system. It was all new engineering. And guess what? Now it's got a bunch of first article issues. And then we ended up sending our own team to fix it.
Yeah.
So like we deployed 5 of our own best engineers up to Seattle. We sat with the vendor. Vendor told us it would take it 2 to 3 months to fix the thing, and we got it fixed in 2 weeks. And then we're looking back and saying, well, we thought we'd save money on this thing, but it actually turned out that outsourcing it was the most expensive thing we could have done. And we ended up insourcing it at the end of the day anyway. So
yeah.
We've done a couple things both ways, and we look back, which is like, if it's custom engineering, we'd rather do it ourselves.
Well, I was with RJ yesterday and talking about Rivian, and they went from 17 control modules, ECUs, and they went from 17 to 7. They saved 1.7 miles of wire, which turned into about 20 kilos. And I asked them, well, how'd you do that? Well, we just designed it ourselves. We're going vertical on everything. And that is the way to win. And you've still got people pumping out, experts that say, oh, well, outsource, that didn't do real well for us on the Chinese deal. So it's got to be something where there's got to be some kind of a turning point, a tipping point where all of a sudden, oh yeah, that's old and we can't do that, and we got to do it ourselves. We've got to do it in-house. So, and this is another shining example. Do it in-house.
Do it in-house, yeah.
Well, apparently we're going to go inside and look at the simulator, I think. Yep. Okay, I'm getting a big. There's a lot of people telling me basically to shut up. Okay, good. Let's move on.
Great, let's do it.
Okay, so I'm here with Geppetto, and we're going to have him jump into the simulator. Simulators are really kind of important. You really want to try out the airplane with a computer as opposed to the old days jumping into a plane and keeping your fingers crossed. So Geppetto's going to show us a little bit about what's going on and how this thing actually works. But before that, can you give us a little background? I mean, I just saw your Winnebago jacket.
Yeah.
I'm really impressed. You got more stickers and patches than I've ever seen, period. Yeah. So why don't you give us a background on your life experiences here?
Sure, yeah. I studied aerospace engineering at the Naval Academy. Once I graduated, they sent me to flight school, and I flew the F-18 Super Hornet operationally for 3 years. After that, I went to test pilot school at Patuxent River, Maryland, and then did a 3-year test tour at VX-23 in Maryland. Then went to a department head tour at an adversary squadron in New Orleans, where I finished up my active duty time flying adversaries, and I'm still a reservist with that squadron in New Orleans, currently flying the F-5N Tiger II. I joined Boom a little over 2 years ago, and I'm the chief test pilot now. I've flown XB1 7 of the 8 times, and we're getting ready to do it again soon.
Wow, cool. Adversary, that sounds Interesting. I never heard that term before. What exactly is that?
Yeah, we're the bad guys for the good guys training. So,
oh, I see.
Yeah, we do threat replication based on the training objectives that the fighters are trying to get that day. We replicate the threat as best we can so that they can make it as real as possible.
So you're the Mavericks, basically. If we look at Top Gun, you're the guys trying to shoot them down.
I'm a Viper in Top Gun, right? Right.
Very good.
Yeah.
Very good. Yeah. Well, why don't you give us a little description of what's going on here?
You can take it off, freeze. All right, so XB1 design feels a lot like a fighter aircraft. Center stick with throttles on the left, as opposed to a yoke like a bigger airplane or something, or a side stick like Overture's going to have. The cockpit layout is pretty simple. You can see I've got everything I need to reach just right at my fingertips without even having to lean forward. Oxygen control is back here, and then all the circuit breakers, one on each side, so I can, if there's something that doesn't have a switch, I can pull the circuit breaker, or I can know if there's been an electrical fault there. The flutter excitation system we don't have modeled in the sim, so this is just kind of a 3D printed placeholder, but this is the interface I use to work with the orange wingtips on the vanes to spin them to inject the frequencies into the fuselage so we can measure the modes and the damping. Electrical control panel, hydraulics, fuel control, and environmental control system. All the avionics, these two are commercial off the shelf, and then this one is custom made. So this shows me everything I need with my air data, airspeed and altitude, and then my engine parameters, my fuel, what my flight control automatic fuel systems are doing, and then any crew alerting system messages will show up here. You can also see I've got a camera right here. It may be difficult to see from where you're standing, but once you get in here, you'll see how difficult it is to see out the front. The reason for that is it's shaped for supersonic flight. It's designed for that. So we kind of traded that with the ability to see out the front, and we got around that by putting two cameras on the nose gear. One goes here, and then I can actually bring up another one here. So there are two separate cameras with two separate wiring systems going to two separate displays. So a truly redundant system, with the thought being if a bird takes out one, then I've still got the other one. And this is kind of one of the big things that XB1 is looking to demonstrate for Overture, is the ability to land an aircraft without actually seeing the outside. Overture will likely have a similar shape. The Concorde got around it by drooping the nose. Yeah. A heavy system and something that can fail. Camera technology has really improved since then, and so we've incorporated that in XB1, and I've demonstrated that I can safely and effectively do that, and then we can carry those lessons over to the development of Overture. Over here, landing gear handle, and then flight control systems. We've got a stability augmentation system on all three axes, as well as an aileron rudder interconnect. That helps with adverse yaw. When I deflect the ailerons, the downgoing aileron increases the lift, but it also increases the drag. So even though I want to go that way, the nose initially goes that way, or the opposite direction. The ARI kind of automatically helps me with that. Engine start buttons, and then the throttles, and then just another set of circuit breakers over here. So relatively simple cockpit.
Yeah, piece of cake. Yeah. Wow. Well, this looks a lot more complicated than anything I've ever seen before. So, So why don't you give us can we take it off and
sure,
and make things happen?
Yeah, absolutely. It might be easiest to see the screens if we go.
Yeah, I'm gonna
lights
move
off.
back here. Yeah.
All right, so a normal takeoff, I'll check the engines individually with the brakes held, make sure they're healthy, and then I'll spool the engines up halfway until I'm ready to go. I'll release the brakes into mill while I'm monitoring the engine parameters, and then into max afterburner. Once the afterburners light up, get quite a bit of acceleration out of it. At 120 knots, I throttle back a little bit, and then at 150, smooth rotation. Now you can see the value of the camera as I can't see out the front of the nose anymore. But once the landing gear are retracted, that camera goes away. And then once the landing gear are fully retracted, I can accelerate above 225 knots. Before pulling it out of afterburner.
What does it look like when you go supersonic, or does this?
Sure, yeah, we can do that. So our planned supersonic test point is 34,000 feet and Mach 1.1. So in order to get up there, I will climb at around 350 knots until, so I'm looking at this airspeed here, until I hit a Mach number of about 0.85. We haven't fully expanded out to that envelope yet, but we'll get most of the way there tomorrow, or on our next flight, rather. So this is kind of our best climb speed. Our vertical speed is over on the right, approaching 5,000 feet per minute. And then off to the right, you can see Edwards Air Force Base. That dry lake bed is where all the, this is where Chuck Yeager broke the sound barrier in, was that 77 years ago now?
Quite a while.
Yeah. And then the supersonic airspace that we're going to be flying in is named for that airplane. It used to be called the High Altitude Supersonic Corridor. It's now called the Bell X-1 Supersonic Corridor. But the dry lake bed over there is where the X-15 landed, and the space shuttles landed at Edwards. So there's quite a bit of history there. It's a really cool place. So as we're climbing up, I'm keeping an eye on cabin altitude, so the cabin pressurization keeps it at 8,000 feet or so until we get above about 23,000 feet. And then it maintains a 5 psi differential between inside and outside. So above 23,000 feet, you'll see this number slowly start to come up. Our fuel transfer is automatic. Took off with a little bit of gas in the forward tank, and then transferred it into the from the forward into the main, and then the bottom into the main. Now this indicates that I'm transferring out of the aft tank into the main tank. And then the main tank feeds fuel to all 3 engines simultaneously.
So you were mentioning range. What sort of range would this thing have?
That's a good question. I think our last flight was a little bit slower. We got about 460 miles. I think I'm not completely sure on that number. It's not something we typically track for this program. We have ways of figuring out what the maximum range would be, but that's just not one of our test objectives for this project, and so we haven't done that work.
Yeah, XP1 is really about supersonic aerodynamics, build a safe airplane, then go fast. And we didn't optimize for making it go far because there's no point. Like, Overture, we're going to have over 4,000 nautical miles of range.
4,000 miles. Yeah.
Well over 4,000. You know, the stretch goal is to be able to do Tokyo, Seattle nonstop, which is about 4,250.
Yeah. How much time do you think that would take then from Tokyo to Seattle?
4.5 hours.
4.5 hours. That beats the daylights out of a half a day. Yeah. Personally, I absolutely loathe travel, especially when you're going huge long distances. And I mean, time is money, and I'm just small potatoes, and I see days slipping away. When you get older, days mean a lot more. Time means a lot more. And to me, this is just the right way to do things. I don't even like connections at all. So at the end, this is the way to go.
I hate to interrupt, but I'm about on condition here for our what our first supersonic test point is going to look like. So we're planning on doing it level. There's a couple reasons for that. One, to prove that we have the performance and we're not just diving into the point like airplanes. Some high subsonic airplanes can achieve supersonic flight in a dive, but they can't sustain it. This one will sustain level supersonic flight. Also, going through the transonic region, there's a lot of unknowns, and so if I can minimize what the demands I'm putting on the aircraft as we go above 0.95, then it kind of minimizes the risk. Yeah. So we'll make this turn. We'll get pointed back toward Edwards, and then we'll bring up the throttles and get going. So now I'm within the airspace that I'm allowed to do this test point in, where we've been given a special authorization from the FAA to fly supersonic over land. Roll out and start the acceleration. And this is the Mach number you're looking at here. So 0.95 is faster than anything cruises at today. Here we go through Mach 1. You can see the rate of acceleration kind of decreases, and now as we get on the other side of it, you'll see the numbers start to tick up a little bit more quickly again. That's due to the transonic drag rise. There's a lot of drag right at Mach 1, but then not quite as much at 1.1. So here's 1.1. This is where I'm going to look to stabilize for our first supersonic test point. And then later, once we prove that the aircraft is safe to fly here, then we can bump the throttles up a little bit more and continue to accelerate. In the controls, I can feel a little shift. I actually need a little bit more aft stick, so I can trim that out as we transition from subsonic to supersonic. Normally, as you accelerate, you need to trim down, but the center of pressure is shifting over the aircraft, most notably on the horizontal tails, and so that causes a shift in the control stick. But at this point, it's at least our predictions indicate that everything's pretty well behaved, pretty smooth, pretty easy handling qualities. Because this is what the airplane was designed to do. It was designed to fly supersonic. This is where she's happy. So you can see we're at 1.3 and we're still continuing to accelerate, and then pretty soon we're going to run out of airspace, and then be ready to set up to land.
Yeah, looks like you're over the lake already.
Just about.
So what is landing speed on this? 200 and something?
About 170 knots.
170?
It's weight dependent. I reference the angle of attack, or AOA, which you can see here. Target is 12 degrees, so I'm a little bit slow right now. And then I've got this E bracket right here, which is a nice useful tool. Yeah, well, so that's giving me my AOA indications. So with that center of the bracket being 12, and then the top of the bracket being 14, and the bottom of the bracket being 10. So that gives me a nice indication of what my speed is doing, without having to read and interpret a number.
So have you already released the landing gear?
Yeah, the landing gear's down. I've got 3 down and locked here. You can see I can't actually see the runway from where I'm sitting, but with this camera on this display, it's almost as if I'm just looking straight through the aircraft.
Actually, it's better because you got things that you don't get when you're trying to land visually.
Yeah, it's almost like a HUD in the F-18.
Yeah.
So approaching about 30 feet above the ground here, we'll start the flare, start bringing the throttle back, and then just slow down and let the ground come up to meet me. Bring the nose down, and now I can see the runway through the windscreen. And start coming on the brakes, and I've got the whole runway in front of me to come to a stop. So now you've seen it once, you should be an expert at it. You're ready to give it a try.
Yeah, right. I can see this going nowhere fast. I'm going to look like a fool on this one. Okay, so we're down here right in front of the plane, and what we're going to do is we're going to cross the FOD line. We've taken everything out of our pockets. The only thing we got is attached to us, like the microphones. That red line is a big deal, and I don't want people from Boeing saying, oh, you crossed the FOD line. We took everything out. Everything's good. We're golden. And now what we're going to do is we're going to get a description of the aircraft, and you're going to find out new things that you never saw before, starting with the pitot at the front of the aircraft. So why don't we give a description of what's going on with all these different features?
Why don't I start with what makes a supersonic airplane different than any other airplane? And the reality is it's kind of easy to make an airplane that goes really fast. It's going to be long and skinny. It's going to have little short wings. And so long as it's going to have engine power, it's going to go supersonic. It's also pretty straightforward to make an airplane that takes off and lands subsonically. The best subsonic airplanes are going to have big wide wings, and they don't need to be that pointy. In fact, making them pointy makes it harder. So the hard thing about a supersonic airplane is it's really two airplanes in one. It's got to go fast, and it's got to be able to go slow. And as we look at a lot of the details of what we've done on the XB1, it's about doing high speed and doing low speed takeoff and landing safely. So for example, if we look at the nose of the airplane and you look really carefully, it's not actually perfectly conical. It looks kind of like it's a cone and somebody sat on it. And that actually makes a major contribution to stability for takeoff and landing. We spent about 2 years working out that nose shape and how to balance low speed and high speed aerodynamics. But speaking of aerodynamics, because this is a test airplane, and everything we're doing on it, we're getting new data for the first time. On a production airplane, you're going to find that there's something called a pitot tube, which is basically an airspeed sensor, and it's going to be mounted kind of up close to the airplane somewhere. For a new airplane, we don't have the calibration yet, and so what we're looking at on the nose of the airplane here is basically a ram air pressure sensor. So air goes down the center of this tube, allows us to measure pressure, and that allows us to go calculate the speed we're going. And we've also got a couple other vanes on here. So this is basically what's called a beta vane. It'll allow us to measure the angle of the nose relative to the oncoming airflow, sort of the yaw angle, the side slip angle. And we've got one over here that's what's called an alpha vane that'll allow us to measure the angle of attack of the airplane. So the angle of the flight path relative to the oncoming airflow. And again, those are way out in front of the airplane, so they're in clean air, not affected by what the airplane is doing itself. And that allows us to get much better data until we would have calibration for the rest of the airplane.
This is the first time that I've stood here and looked. Do you have a lifting body? I see an arc that's...
You kind of see the chine follow the airplane back.
Right, yeah.
Earlier configurations of the airplane actually had the leading edge of the wing come much farther forward. But that was involved in that trade study that Blake alluded to. We iterated numerous times on how far forward the wing came, in combination with exactly what is the fineness ratio and the shaping of the nose in the front. And actually the shape of the nose has a lot to do with the directional stability of the airplane. So we iterated those two variables and arrived at a configuration that maintained low speed stability.
Yeah. So the way a supersonic airplane with a triangular, what's called a delta wing, generates lift is very different from what a subsonic airplane does, even when flying subsonic. So a delta wing uses something called vortex lift. And so if everyone thinks back to high school physics, you remember Bernoulli's principle that says that higher moving airflow is going to be lower pressure. And so if you create a swirl of air, because it's moving, it's going to have a pressure drop. And so that wing, the leading edge of that wing will generate a vortex over top of the wing, and that generates a low pressure region. You get low pressure above the wing, ambient pressure below the wing, that delta in pressure, that's what creates lift That's how the airplane flies. Now, it turns out a lot of parts of the airplane will generate vortices. And you have them in good places, it's good. You have them in bad places, it causes problems. And so if you had a perfectly conical nose, it turns out it's gonna shed vortices in relatively unpredictable ways, like very sensitive to small changes in direction. And those vortices, if you're kind of coming in a crosswind, can actually go across the nose from one side of the airplane to the other. And it can end up creating a low pressure region next to the next to the vertical stabilizer, which what the vertical stabilizer normally does is weather vane the airplane. It keeps the nose pointed in the direction the airplane's going. Well, because if it slips out to the side, you get pressure on the side of the tail, pushes it back in like a weather vane. Well, if you get a vortex in the wrong place, it can actually have the opposite effect. It makes you kind of go sideways, and that's what we call a bad day. And so this specific shape is basically results in very stable, very predictable vortex formation, such that we don't start to get sideways even at small angles, and that prevents us from having kind of further stability issues. And that is, like I was saying before, on the aerodynamics of a supersonic jet, it's all about balancing high speed and low speed. And on Overture, the big airplane, it's about balancing high speed, low speed, and quiet. Because those things all are kind of in conflict with each other, and you got to find the innovative designs that are good enough at everything.
Cool. Wow. There we go.
The other thing we can notice, kind of looking here at the airplane, like if we stand in front of it, maybe we can come around and just kind of shoot down this way for a second. So you can see the shape of the nose. You can also see the windscreen, and there's not a lot of windscreen there. And so as you saw in the simulator, the natural forward visibility is not great, and so the pilot needs a way to see the runway. And on XB1, and the way we solve that is with cameras. So Nick's showing us there. We've actually got two cameras, and they're separated by about the wingspan of a bird. So if a bird takes one out, it probably won't take the other one out. And Overture will have an even higher redundancy level version of a similar thing, and that feeds the augmented reality display for the pilot.
So if you'll notice, these aren't looking straight forward. They're actually angled down slightly, and that's our approach angle. Right. So we come in at that 12-degree approach angle, which you just did in the simulator, and that's so that is looking straight at the runway on approach.
So your landing gear, is that your own, or is that, because I've never seen quite that?
So this is a little bit of a hybrid, but it is a bespoke design, just like the main landing gear are. This nose landing gear is the drag link here and the main trunnion are all custom designed by Boom. The internal components are actually salvaged from an F5 fighter aircraft, and like this steering actuator right here is a component that was originally designed for the T-38. So it's a little bit of Monster Garage, but lots of refined engineering work went into reverse engineering how those systems work, and then designing a bespoke way for it to interface with our airplane.
Yeah.
Cool.
So one of the challenges of the landing gear on this airplane is just the packaging. And so we got a long, skinny airplane. This is originally, we designed this to go Mach 2.2, about 10% faster than Concorde. And that results in, it's hard to get everything to just fit in the airplane like the landing gear. And that drove us to a pretty challenging, particularly the main landing gear design. And this is one of the big learnings for me and the team is just how difficult landing gear can be. You might think, oh, that's not the hard part of an airplane, that's just the part that drives. But the packaging is difficult, and then the loads are difficult. So the main landing gear can take about 200,000 pounds of load in a hard landing, and it needs to be usable again after that.
Yeah. Well, one of the things I'd like to do is bring the camera over here, look at all of this, and look at the door that it's going into. So that's kind of one of the trick things. Trying to get big things into small holes is one of the tricks that you have to learn if you're gonna design aircraft. And you can see that this has got a lot of mechanism so that this is gonna come up, go back, and this door is gonna come and seal. So this is quite the mechano set here.
Yeah, so the way this works kinematically is that there are a couple of doors here that open. And so those open, and then it retracts forward. like that.
Ah, okay. So I didn't see the other door. I just saw this and that. So
Yeah. Yeah, the kinematically, the nose gear is the simple one on this one, and the main gear is the more complicated one. We're happy to go in there and take a look at it. And then on Overture, it's one level more sophisticated than this, where the getting the gear to package compactly aerodynamically is a big deal for efficiency, and we'll likely actually suck up the struts, and so this portion will compress as the gear retracts, so it can fit into a smaller space up in the airplane.
Okay, so now we're moving down and having a look at some of these other openings and whatnot. So this, I'm assuming, is to open the canopy?
That's right. So we talked about earlier, but XP1 does not have an ejection seat, but it does have a jettisonable canopy, both in flight and on the ground. So if there was an unfortunate accident and there was an incapacitation, or the cockpit were to jam for some reason and not be able to be opened from the inside, you can just pull that red lever and the canopy will
pop off.
You know.
And so there's a mechanism similar to that inside?
That's right. That's right. This is only external access, but that system is duplicated for the pilot inside the cockpit.
Okay. So moving further back, we're looking at the wing that you've got here, which usually on commercial craft you've got a big radius here, but there's nothing here because that would probably give you more drag than you're looking for. This is not an easy trick. This is all carbon fiber, right?
This is all carbon fiber. Everything that's
Okay,
painted
so
white, aside from the landing gear, is carbon fiber.
Okay, well, it's a lot easier to do in carbon fiber than it is in aluminum.
Yeah, that's right. Carbon fiber is one of the big enablers of commercial supersonic. Yeah. You know, and actually not primarily because of the weight savings, primarily because of the shaping. Like you tool the whole piece you want to make, and you can make it very precisely, the exact same sophisticated shape that you want. And doing this out of aluminum with anywhere close to this surface quality would be just prohibitively expensive.
Anyway, you just can't do it. So at the end of the day, you're looking at, and another thing I like about carbon fiber is it's now a stone. They're going to always come out exactly the same, and they're not going to move. And that's kind of handy as well. So now you've got a whole bunch of access doors. What are they for?
Most of them are system access panels, and some of them are fuel access panels. So those two right there go into a bay that is filled with avionics equipment. These two right here happen to be into a fuel tank, and we actually refuel the airplane from the access panels on the top. There are 5 fuel tanks in XP1. They're longitudinally distributed down the airplane, and there's a flight computer in the aircraft that automatically manages which tank we're drawing fuel from at a given time to control the center of gravity.
Gravity. Okay.
Yeah, the faster you fly, the more the center of pressure, basically where the lift is in the airplane, moves aft. And so to keep the airplane balanced, you need to move the center of gravity. And so effectively, as we accelerate, we pump fuel backwards, and as we decelerate, we pump fuel forwards.
Cool. So now we're into well, we're not allowed to look at that.
Well,
but
we can look in the front. And this is actually a pretty interesting thing to talk about. So a thing a lot of people don't realize is there's really not such a thing as a supersonic jet engine. They're all jet engines are subsonic on the inside. And effectively, you need a supersonic to subsonic converter on the front and a subsonic to supersonic converter on the back. And that's what an inlet and a nozzle is. And so what we're looking at here is the inlet, the supersonic inlet. And this is, you can think of it as a no moving parts supersonic air compressor. And the goal is basically to take the kinetic energy in the oncoming supersonic air and convert it into pressure energy, because you can recover that back into thrust on the back end of the airplane. And so the way this actually works is it's pretty darn neat. Whenever air hits a surface that's moving supersonic, it creates what's called a shock wave. And a shock wave, all a shock wave is basically a band of hyper-compressed air. And you can kind of imagine, imagine a group of people standing around having a conversation. If someone's running at them and you can see that person coming, you see them coming, you're like, well, I'm going to get out of the way of this crazy person. You start moving. And then so if you have a collision, it's very gentle. And that's what subsonic flow is like. The air, there is a pressure wave that's moving faster than the airplane. And therefore, it starts to kind of effectively it's saying like, hey, something's coming, start moving. And that's subsonic flow. Supersonic flow, the airplane is actually outrunning the pressure wave. And so the air is basically the airplane is whacking into air that didn't start moving before it got there. And so what happens is it compresses the air. And those little bands of compressed air are what are called shock waves. And shock waves stack up, constructively interfere, that's what causes sonic boom. But you can use them usefully, as when air goes through a shock wave, it actually slows and it compresses. And so this lip here creates a shock wave that comes off down like this. And then the rest of the oncoming airflow, as it goes through that shock, basically turns and compresses. And the idea here is that but we're going supersonic here, but we're going about half the speed of sound by the time we hit the front of the engine. So the engine just sits there doing its job subsonic, doesn't really even know it's going supersonic. And on the back end, we have a nozzle that then basically takes this high pressure, hot supersonic flow, expands it and accelerates it back into supersonic flow in the back end, and that's how you get it thrust out of the propulsion system.
And we really paid for our tuition on this thing. This was one of the hardest attributes of XP1 to design. It would be easy to make a larger capture area because you're going to more gently conform the air to the conditions that the engine needs at its front face. But if you have a large capture area, that causes a lot of drag. So you can't go fast if you have that large capture area. So you really got to find this nuanced, detailed design point where it's small enough to be less draggy and efficient enough to condition the air. And that's a very hard thing to do. We got it wrong 3 or 4 times before we got it right. And so we had to iterate on this, refine the leading edge shape, and actually add auxiliary suck-in doors that give basically when the engine's drinking through a soda straw because the inlet is so small. So when we're going slow and you don't have that large ram effect of flying through the air helping you, you need auxiliary paths to help augment that air intake into the engine. So we figured all that out, and that took a year and a half worth of ground testing. But the capability of the team that designed and iterated on that inlet is truly impressive. They have fought the hard lessons and become really smart about it.
So the engine is going to be the same as every other jet engine as far as the mechanics and whatnot?
In that regard.
Yeah.
Yeah.
So for those who are not jet engine kind of people, it's suck, squeeze, bang, blow.
Yeah.
That's kind of like the how that engine works. So you suck here, bang is the inside, or squeeze is inside. That's where your fans are coming together, and then bang just means the explosion of fuel and whatever air you've got in it, and blow is basically what's shipping the aircraft along. Right. So
it's just like the principle is the same as a piston engine in terms of you're doing, but in a piston engine it happens all in the piston, right? It happens all in the cylinder, and it's the same place, different parts of the cycle. And a jet engine it's a very similar set of physical processes, but instead of being laid out in time, it's laid out in space. So there's a compressor that's continuously compressing, there's a burner that's continuously burning, there's a turbine that's continuously extracting power from that, and then there's a nozzle that's expanding the flow out the back.
Right. But at the end of the day, this is, and pistons are like this, and one's inefficient, the other is pretty efficient because it never does anything but spin. And that's why you get a lot more life out of a jet engine than you will out of a piston engine. It can't even come close to competing. Too many moving parts. These things here, all it does is spin around in a circle. Now we're underneath here, so let's have a look at this. Yeah,
so feel free to kind of watch your head, but you feel free to kind of get up in there, and kind of the first thing to notice is there's just so much going on in that landing gear bay. So the landing gear is safety critical. When it needs to be down, it needs to be down. When it needs to be up, it needs to be up. And building this such that it's high reliability drives a lot of the complexity. And this is actually our kind of 2.0 landing gear design. We've done the landing gear design of this airplane twice. And as we went from 1.0 to 2.0, we deleted about half of the parts.
Yeah. And
we're able to make it much simpler and much better.
This is a really tough packaging challenge. And so it forced us towards high loads, exotic materials. The main leg right here, so this is probably the most highly loaded component in the airplane. This is made from AirMet steel. It's an AirMet weldment. AirMet 100. It's 300 KSI heat-treated steel. And when you're working with metals with that kind of capability, and then you need to do a welding process on it, you're worried about the residual strength through the joint. It becomes very important. It's difficult process-wise, so we had to figure that out. This drag link right here is solid titanium, grade 5 titanium billet. And this is essentially the shock absorber for the airplane. So one of these on each side, they're identical left and right. And this is what arrests the vertical descent rate when we hit the runway.
I'm just looking at how do I squeeze all this stuff into that little teeny tiny box. And
yep. If you look, the ceiling is we made a ceiling out of hydraulic tubes and wiring. It was a tough challenge to get everything to fit.
Well, one thing, you won't be getting anybody in here like a stowaway.
I don't think they'd enjoy the ride.
I think you couldn't get a rat in here, let alone a human being. Yeah, this is really tight.
As you can take a look at some other components if you're curious. So we have 2 hydraulic reservoirs. There are dual redundant hydraulic systems on the airplane. You've got one reservoir right there, nestled in right above that landing gear leg. The other reservoir is right here. We have an emergency DC pump should we lose the engine's capacity to build hydraulic pressure. And that's actually powered by DC. It's a 28-volt DC backup hydraulic pump. You see a lot of manifolds in here that condition the flow, filter the flow. This box up here is actually the generator control unit, regulates voltage coming out of the generator on the engine.
Does this have a rat, no?
No ram air turbine. Our backup is that DC pump up there.
Cool.
Yeah, we are expecting to have a rat on Overture though.
And the airplane is equipped with anti-lock brakes. So they're carbon brake stacks with tremendous energy capacity for their size. They are probably the highest energy capacity brakes in that wheel diameter size on planet Earth. Rated to over 12 million foot-pounds of energy for a 13-inch rim. And we have anti-skid on them as well.
Wow, that's kind of amazing.
Yeah.
Do you make those yourself, or are you buying them?
No, those are commercial off the shelf, but they're a military derivative.
I see. Wow. Well, this is really quite amazing, actually.
Yeah. There's a surprising amount of complexity in the airplane, and we tried wherever we could not to literally or metaphorically reinvent the wheel. So we could get wheels, brakes, whatever off the shelf, we would do that, and then still strove to keep the airplane as simple as we possibly could. The best part is no part, the best system is no system, and yet the requirements of a safe, reliable supersonic jet actually drive a surprising amount of complexity into the airplane. This is a much greater percentage of the complexity of an airliner than you would expect for an airplane just of its size.
Well, I've worked on a lot of commercial and military aircraft, and I can't think of anything that I've seen that would be topping this. This is pretty amazing, actually. Really amazing, actually.
Yeah, and the downside is how long it took and how expensive it was. We would have loved to have been done with the project a year ago, but the plus side here is just like the amount of knowledge that the team that built and tested this thing gained. Designed, built, and tested it. The tuition is just world class. You can't get it anywhere else unless you've done something like this.
Just out of curiosity, like I said, we work on a lot of different projects, and one of them, your commercial plane, if it's at 1.8 Mach?
1.7.
1.7 Mach. That would fall into a category that the Air Force would be kind of interested in. Is that why they're funding you a little bit? Are they looking to?
There's some pretty interesting defense applications. Like you think about the military portfolio today. We've got fast fighters, we've got fast bombers, but if we want to move people, the state of the art's like a C-130 or a C-17, and these are pretty slow airplanes. And so the obvious application is things like VIP transport. Can we get the Secretary of State or a congressman someplace important quickly, where in-person influence matters? getting special forces somewhere. That's another situation where you get the special forces where they need to be in half the time. It could change the outcome. Yeah. And so medevac is another one. Can we get a soldier evacuated to life-saving medical care? So there's a small number of use cases that really matter for transporting people and things when time is of the essence.
Well, time is everything. Money doesn't really count if you can't buy a second back for $1 billion. So that's what I'm looking at here. This is ideal for getting 60 of the right type of people in the right place at the right time would make a gigantic difference.
Yeah.
Okay, so let's slide out of here.
Watch your head.
Yeah, I'm watching my head. I'm watching your plane too. I don't want to get a bill
if your head could take the plane out, we probably got a bigger problem. But actually, if we want to go around to the other side, it's mostly symmetric, but we've got a couple panels that are open on the other side, and that might just kind of afford a bit more of a view.
Just watch your head on this antenna right here. Yeah. Yep. So this is the systems bay. If you kind of just peek in there, you can kind of see some flight controls components. These are actually the 3 engines throttle cables right here. So mechanical signal running back to the 3 engines. That's part of the flight control linkages, both in cables, push rods, and pulleys that run throughout the airplane. There's up above you is the environmental control system pack. It's an air cycle machine that conditions hot compressed air from the the compressor in the center engine. And it's a very powerful air conditioner that brings it down to a very comfortable cockpit environment and keeps the cockpit pressurized.
What's that? I've never seen that kind of thing.
That's just a louver that's outlet flow for secondary air that comes in via this inlet. So that environmental control system has basically it looks like a turbocharger in a car, and it's taking air, it's further compressing it to heat it up more so, then it cools that off in a compressed state, and then it expands it and it becomes refrigerated air. Huh. So it's basically a car turbocharger, both a compressor and a turbine, and you cool it in the middle of that cycle, and that makes very highly refrigerated air.
So what do you do with that?
That's what's used to keep the cockpit pressurized and comfortable temperature. And that inlet flow and outlet flow is that air that we use to cool that air in that intermittent compressed stage.
Got it.
So another thing that's interesting to notice, Nick said throttle cables, and people might be surprised to find that there are cables on this airplane, and we kind of sit halfway between a fully manual flight control system and a fully fly-by-wire. Overture is going to be fully fly-by-wire, and what we wanted to do on XB1 is to have the predictability, reliability, and simplicity of a manual control system, but we wanted to start to build our engineering expertise in digital flight controls. So we actually have a 3-axis stability augmentation system on the airplane. We started out with 2, we ended up adding a 3rd axis. And so there are basically cables and push rods from the pilot's stick all the way back to the hydraulic actuators that drive the ailerons, the rudder, the horizontal tail. But there are, in series with those, we have digitally controlled actuators that are driven by flight control computers that basically provide better handling qualities on roll, pitch, and yaw. And yet those make the airplane easier to fly, but it's still flyable without them. And so we actually did the first flight without the stability system turned on. We'd had it in pitch and in yaw, and we thought roll was going to be fine. Turned out pitch and yaw were great, and roll was, with the pilot in the loop, it was more challenging than we thought it would be. So we ended up adding a 3rd axis stability augmentation system to the airplane. And that's a lot of what went on between Flight 1 and Flight 2. And again, it just goes to the capability I'm so proud of in this team. We designed from scratch and implemented and tested and then flew a whole roll stability augmentation system in just a few months.
That's amazing. That is amazing. How many people have you got on board now? You said you had 50.
Yeah, the XB1 team is about 50 people, including engineers, technicians, mechanics, pilots, the whole crew, and the entire company is about 140 people now, and that's it's probably about 80% technical A thing I've come to believe is just, we said this before, small teams run circles around big teams. You don't need as much overhead, you don't need as much communication infrastructure, it forces, keeping things small forces innovation. You learn how to do things more efficiently.
It's easy to, it's not so easy to hide either. One of the things that I see when I come into big companies is 20% of the people do 80% of the work. And there's a lot of folks wandering around like this or like this. I mean, and quite frankly, when you get into the bigger the organization, the more you see of that. And that, again, that pretty much wrecks a culture. So anyway, we're moving further back here. Watch your head.
So you can see on the panels here, as Blake said, everything white is essentially carbon fiber. And when it gets into metallic here, this aft section is made out of grade 5 titanium. And that's mainly for thermal reasons, because this is tightly wrapped, shrouding the 3 engines on the airplane.
And this
this
airplane
is
has
something I would never do.
And so the four-body shaping is extremely important to control those vortices. Back here, all of this exists in the boundary layer of the air flowing past the fuselage.
So this is actually, there's nothing here, and, the air is here.
Believe it or not, these screws do not meaningfully slow the airplane down at all.
Cool.
Yeah.
Yeah. So boundary. So basically, as the air flows over the airplane, friction between the surface layer of the air and the airplane, it basically start to grab onto the air and pull it with it, and that creates what's called the boundary layer. And at the front of the airplane, the boundary layer is very thin, but by the time you get to the back of the airplane, the boundary layer is very thick. And you can think of the boundary layer as kind of moving along with the airplane. And so having things that protrude into the boundary layer don't create much drag. So back here, we're not sensitive to the surface quality of the airplane the way we are with the front. Another way you can see that the boundary layer manifested is so engines don't like uneven airflow. They like very smooth airflow going into them. And so because the boundary layer is moving at a different speed than the ambient flow, the simplest thing to do is to keep the engine intakes out of the boundary layer. So if you look, for example, above that engine intake, you can notice there's a gap.
Yeah.
So there's a gap between the engine intake and the underbody of the wing, and that's what's called a boundary layer diverter, and that's keeping the inlet in a kind of clean free stream. So it gives you some idea of how thick the boundary layer is from the start of the wing to the top of that intake. And if you look up on the top of the airplane there on the dorsal intake, you notice that the boundary layer diverter is much taller. And that's because, so from underneath the wing, there's only the boundary layer that's accumulated from the front of the wing to the intake, versus on the top of the airplane, you got all the way from the nose back to that inlet. So the boundary layer's gotten a lot thicker, and the inlet needs to be that much further offset from the body of the airplane.
One of the things that we were talking about engines, boundary layer is the only reason that a turbine can work, because the temperature inside the boom part is astronomically high. And if it was all by itself, if we didn't have a boundary layer, all the turbine blades would melt or disintegrate, whatever. So the boundary layer is what basically keeps, even though it's really hot, it keeps the blades from melting or degrading into dust.
Yeah, the technology that goes into turbine blades, is fairly impressive. At this point, it's decades old, but it's still impressive. The blades are hollow on the inside. The ambient temperature around them is actually above the melting point of the metal. Right. And like you were saying, there's cooling air that goes in through the center of the turbine blade, comes out in little porous holes in the front of it, and then that cooling air envelops the blade and prevents it from melting, which would otherwise, if you turn the cooling air flow, the whole thing would just melt to pieces.
Yeah. So let's go all the way aft and see what we've got left. So the one thing I did notice when I was flying the simulator was that little teeny tiny rudder can really make a big difference.
What's surprising is that one of the things we learned in flight test, the rudder looks kind of comically small, for an airplane of this length. It actually had more, by about 20% or so, more authority than predicted by CFD. So these are the kind of things that you can only learn them in flight test, and we were able to measure that in our test flights.
Another thing that's sort of interesting to point out on the back end of the airplane is so we've got the horizontal tail here, and that pivots, and that's what controls the nose up-down attitude of the airplane. And as you accelerate supersonic, the tail actually loses control authority. So on a subsonic airplane, you'd often find that most of the horizontal stabilizer is fixed, and you just have an elevator at the back like this. Yeah. And this is what's called an all-flying tail. So that entire surface pivots, and you can see a little bubble there on that inboard fairing. There is a titanium torque tube that connects into this control surface, goes all the way underneath the engines, and connects this to the other horizontal tail on the other side. So they always move in unison. And there's a fun sort of development story in this. So that this tail is carbon fiber composite. The torque tube and the fitting that connects the torque tube into the carbon are titanium. And we actually built a test tail, took it up to the highest temperatures it would see in supersonic flight, and loaded it up until it broke. And the first thing to fail was actually the titanium, not the carbon. Yeah. So it really goes to just what an impressive technology carbon is, and the design details of it matter. So if you X-rayed this the tail, you'd find that it's not just like even layers of carbon. The stress engineers figured out kind of where the load would be in the tail, and then align the direction of the fibers such that they're strongest where you need to carry load, and light where you don't need the capability. And so effectively there are a bunch of toes of fiber kind of radiating out from that attachment fitting.
Hmm. You're talking about heat. What kind of temperatures are you looking at? External temperatures when you're at speed. Have you checked that out?
You want to take that?
Yeah, below about Mach 1.6, 1.7, the ambient heating that you get from just going really fast is actually not that much. It's not a big deal. The engine section in the back obviously gets very hot because it's close to the hot section of the engines. Yeah. Above about Mach 1.7, you start to see almost an exponential rise in the stagnation.
Somebody's having fun.
Yes, they are.
Above about Mach 1.7 is where you'll start to see an exponential rise in the stagnation temperature that you need to design the airplane to. So for SR-71, which is a Mach 3 plus airplane, its skin temperature would be 700 degrees. At a Mach 2.2 design point, we originally designed the whole structure for about 320 to 340 degrees of capability. Mach 1.7 is about that inflection point where things start heating up.
Yeah, one of the arts of the design process here is we started off targeting Mach 2.2, and then as going through the design process, we found where the stair steps were in difficulty. And as we went to Overture, we said, great, now we can be really pragmatic and be on the happy side of a lot of speed up for passengers, and also on the happy side of things that are like the add cost complexity challenges. And at Mach 1.7, the reasons for that number, on one hand, it's twice as fast as the fastest Boeing or Airbus today, so it's a real significant speed up. And on the other hand, the temperatures at Mach 1.7 are actually the same temperatures that the 787 was designed to, not in the air where it's cold, but on the ground in the desert on a hot day. And that means that all of the material science developed for 787 just transfers directly, and we all know it's gonna work, and we don't have to use anything exotic.
Yeah, using known certifiable material systems, big influence in that choice of Mach number design point.
So anyway, I'm seeing this. We're going too long. He's going to get upset.
Okay.
So anyways, I'd like to thank you both. This was a brilliant time.
Thanks.
I got to tell you, I was expecting a lot, and I got way more than I thought I was going to get. I really am. I'm really excited for you guys. I sent a text and whatnot. When I get back to my phone, I'll find out if I somehow can change my flight plans and whatnot, and maybe hang around. I would like to see this thing take off, but based on what I know is on my calendar, I might not be able to do it. But is there any chance that we could get B-roll?
Oh,
if we
absolutely.
Okay, great.
Yeah, we'll get you B-roll, but there's no substitute like seeing it with your own eyes.
You're
So
absolutely
if you can make it work, it'd be awesome to have you.
Wow, it was a big deal when we flew the 787, and I kind of missed it. I wasn't there. I can't tell you where I was. It was really important, but I didn't get a chance to see it. So I'd really like to see this. You guys have done a fantastic job. Thank you so much.
Thank you.
I really appreciate it. Thank you.
Thank you.
And everybody out there, thanks for watching.